So just a quick recap on what exactly we proved in the previous page. If you start with an m by n matrix A, you can use it to define a linear transformation, which we call T, and then we used A as a subscript, right? That use the matrix itself as a subscript to indicate that you're actually using the matrix A to define the linear transformation, and this is the actual definition. It takes as input some n-dimensional vector x, treats it as a column matrix, and then left multiplies it by this matrix A. And what we proved down here is that that indeed gives you a linear transformation. But now the dual question would be, what if you just start with a linear, like forget about this matrix A, what if you just start with an arbitrary linear transformation? Is there some matrix out there that corresponds to it in the same way? That is, if you start with a linear transformation that goes from Rn to Rm, is it possible that you're really just talking about one of these linear transformations for some appropriately chosen matrix A? And the answer is actually yes, as long as it's a linear transformation, right? So we can actually make this claim stronger. Not only can you always define linear transformations using m by n matrices or by left multiplying vectors by m by n matrices, but you actually get every linear transformation in that fashion, as long as you're willing to determine what the matrix would have to be in order to do it. So that means, for example, this linear transformation up here, there's no matrix involved. There's no matrix A in this question, but there's some matrix A that you can come up with, that if you define this linear transformation corresponding to that matrix, you're just going to get this one. There's some appropriate matrix out there that you could choose that will do the job, right? And we'll look a little bit more at that on the next page. But now let me just formulate this claim that I'm making to you a little bit more precisely. So we're going in the other direction here. So if you start with any linear transformation T, you're going from Rn to Rm, right? This is the most general header for any vector function. But we're going to make the assumption now that it's a linear transformation. We're not going to prove it because that's an assumption that we're making now. And the claim is that there exists some n by n matrix A such that this linear transformation T behaves in exactly this way, right? So it really just takes an arbitrary input vector x and it multiplies it on the left by the matrix A. There's some matrix out there that you can get your hands on if you know what to do, that will really, you can represent this linear transformation in this fashion. Okay, and this matrix, if you can get it, has a name. Well, and it has a name whether you can get it or not, because it's guaranteed to exist, but it has a name. It's called the standard matrix of the linear transformation T. So we'll just say in this case A is called the standard matrix of T. And the notation that we use to write it down is just we write the linear transformation, capital T. That was the notation that we used for it up here, the name. Just write square brackets around it, right? Just they're kind of like matrix brackets, just to tell you that you're talking about the standard matrix that's associated with that transformation. Okay, so let's look at an example. In fact, I mentioned the previous example. Let's take a look at that one. So consider the linear transformation. It goes from R3 to R3, defined by the following rule. T of x1, x2, and x3 is equal to x1, x2, and then the sum of x1 plus x2 plus x3. This is the same example that we just worked with, and we proved in detail that it's a linear transformation. So we're not going to prove that now, but we're going to look at how this claim applies to this linear transformation, right? So this is a linear transformation. What is its standard matrix? How can we come up with a matrix A such that this definition is equivalent to this definition? That's the question. Well, make the following observation. So for any vector x in R3, so x, and we'll write it generally as x1, x2, and x3. So for any three-dimensional vector, we have the following. Let's just write out the definition of T. T of x1, x2, x3 is really equal to this, right? It's going to be this three-dimensional vector. So x1, x2, then x1 plus x2 plus x3. So that's true, but I mean, that's nothing new, right? All I did is just repeat myself. But let's take it a step further now. Let's actually rewrite this in a different form. And it's not going to be obvious why I'm doing this until the end, but at least ask yourself whether you agree that this is actually equal to what I'm about to write down. So for the first coordinate, I'm going to write 1x1 plus 0x2 plus 0x3. And then for the second coordinate, I'm going to write 0x1 plus 1x2 plus 0x3. And then for the third coordinate, I'm going to write 1x1 plus 1x2 plus 1x3. Now, first, you should just convince yourself that that's true, right? Of course, if I get rid of the x2, there's the two terms that have 0 factors. Those are going to disappear anyway. I'm just going to be left with 1x1, which is what I have here. And for the second coordinate, the first and third term are going to disappear, and we'll just be left with 1x2, which is what we have here. And really, these ones imply that the third coordinate is just going to work out to x1 plus x2 plus x3, which is exactly what you have over here. So it's certainly true what I've written, but why would I do that? Why would I bother to do this? This seems like just a really long way of saying what we already know. But the reason is, this is actually looks more like a matrix product, and it actually is. This is the product of a 3x1 matrix, pardon me, a 3x3 matrix and a 3x1 matrix, and that's why, as a result, it is a 3x1 matrix. It looks all spread out because of the extra terms, but there's only 3 entries. This is the first entry, this is the second entry, and this is the third entry. So it's one column with 3 entries. So this is actually the product, and you can check this, and I would suggest that you do that. Pause this video once I finish writing this step down and check that this product is actually correct, or this factoring is actually correct. Right, so I've written this as the product of this 3x3 matrix and this 3x1 matrix. And you can check that it actually works. This is a 3x3, this is a 3x1. The result is going to be a 3x1, and it's going to be exactly this, just using the definition of matrix multiplication. So guess what? This must be your standard matrix. That's how you now know that this is your standard matrix. So therefore, the standard matrix of this linear transformation T is given by 1, 0, 0, 0, 1, 0, and 1, 1, 1. So that gives you one way to actually, one strategy that you can use to identify the standard matrix of a linear transformation. But it turns out this is really not the best way to do it. There's a better way. But I wanted to go through this example because it really shows you what the relationship is between the standard matrix that we have here and the linear transformation, which is defined up here. The definition that defines the linear transformation, this is really what determined what this matrix would be, right? So that's what I want to go through there. And I also want to draw your attention to something. Let's just plug in the standard basis vectors. And maybe I'm even going to this is a bit of a separate section of work here. That's not directly related to what we did up here. So this is kind of just rough work. What would T of the standard basis vectors be? This is a question that we haven't asked yet, but it's going to turn out to be a really useful question to ask. What would T of E1 be? This is E1, right? It's the vector that has a first coordinate of 1 and everything else is 0. Well, what would it be? Just use the definition up here, right? So the first coordinate is just going to be a copy of x1. So you're going to get 1 for the first coordinate. The second coordinate, x2, is just going to be a copy of the second coordinate of the input vector, which was 0. And then the third coordinate is the sum of all the coordinates in the input vector. So the third coordinate is going to be 1 plus 0 plus 0. Well, that's 1. Right? And now what about the other two standard basis vectors? What about T of E2, which is 0, 1, 0? What's that going to be? Well, use the same approach. The first coordinate is just a copy of the first coordinate of the input vector. The second coordinate is just a direct copy of the second coordinate of the input vector. And then the third coordinate is the sum of all three. So you get 0 plus 1 plus 0, which is going to be 1. And then lastly, what's the other one? T of E3. Let's work out T of E3. E3 is 0, 0, 1. And, well, do the same thing. First coordinate is just a copy of the first coordinate of the input vector, so we're going to get 0 for our first coordinate. Second coordinate, just copy it from the input vector, so we get 0 again. And then the third coordinate, add them all up, right? Add up all those 3 points, you get 0 plus 1, and that's what you get. So that's just a bit of side work. And you may have noticed already, that these 3 columns are actually exactly the 3 columns that we see here. So let's identify that. This column here is actually T of E1. Right? This is E1. This vector here is E1, so this is just a more abbreviated way to write it. And now this middle column, the 0, 1, 1, that's over here. So that was T of E2. And then lastly, our third column, that was this one here, which is actually T of 0, 0, 1. And that is no coincidence. That's always going to happen. If you want the columns of your standard matrix, all you have to do is just plug the standard basis vectors into the linear transformation and interpret the results as columns. And then put those columns together and just, you could, essentially this is what happened, right? Just put the columns together and that'll give you your standard matrix, right? We didn't do it that way. We did it a longer way, but this way is much more efficient. Just work out the output from the linear transformation at each of your standard basis vectors, and that will give you the columns of the standard matrix. So let's write that down formally here. This is actually a theorem. So let's write it out in detail. So suppose you have a linear transformation. So suppose T going from Rn to Rm is already known to be a linear transformation. Okay, so let's start with that assumption. Everything I say after this line will not apply to any function that isn't a linear transformation. This only is relevant if you already know that your function t is a linear transformation. Well, here's what the theorem says, though, in that circumstance. The standard matrix of this linear transformation, which is denoted by t in square brackets, right? That's the standard matrix of the linear transformation t. So the standard matrix, which is, I don't know how else to say this out loud, but just saying standard matrix. So I'll just say the standard matrix, which is given by this notation of t, is the m by n matrix given by the following formula. And before I write it down, just notice that I said it's an m by n matrix. So right off the bat, if you have the header for the function, it goes from Rn to Rm. This n, you know that's the number of columns in your standard matrix, and this is the number of rows of your standard matrix. For example, up here, this function goes from R3 to R3. So this is the number of columns. There's 1, 2, 3 columns. And this is the number of rows. There's 1, 2, 3 rows. So that's just an example of that. But so if you have the header, you instantly know the dimensions of the standard matrix. Just take these two numbers, change their order, and you can put them together to get the dimensions of the standard matrix. And the standard matrix is going to be given by the following. Just take the linear transformation t, plug in the first standard basis vector, and that is going to give you the first column of the standard matrix. Then for the second column, you just plug in the second standard basis vector E2. And you just keep doing this until you get all the way up to the very last standard basis vector of Rn. And if your domain of your linear transformation is Rn, that means there's going to be n standard basis vectors. So I will extend this off for an unknown duration. I'll just put dots because we don't know how far it goes, but the very last one is going to be t of En. Okay, and that is the result. So that's true in general. An illustration of that in action is really just this, right? If we wanted to find the standard matrix of this linear transformation, all of this work that we did here, we didn't need to do this. We could have just done these 3 calculations, put those 3 columns together like this, and we would have got our standard matrix. So that's what this theorem is telling you. It's giving you an efficient way to come up with standard matrices of linear transformations.